Hi guys, welcome to the third installment of the stats lesson that I want to give on normal distributions. So today it's going to be a quick video where I'm just going to make two things happen. And the first thing is that I want to connect the table of values for the standard normal distribution that we've been doing over the last two lessons. I want to connect that with the three rule of thumb numbers of 68% for one standard deviation, 95%, 99.7 for 2 and 3 standard deviations away from the mean. So I want to connect the table to that just to make sure that you realize that it's all the same sort of concept with normal distributions. And then I want to do a question which I've been asked by some of my students, where you sort of go backwards, where they give you some probability and you actually need to find the mean and the standard deviation itself. So before I go on, I guess this is more of a recap for now. So if I said normal distribution as a heading, so I really want to start with that first objective of tying in the bell curve as we know it back in year 9 and 10 with the three numbers to what we've done in essentially the standard normal distribution table. So back in year 9, right, you would have gotten, let's see if I can draw this bell curve. That's probably as good as it gets, where you have the mean in the middle, right? And then to each side, if I take one standard deviation away, so this is mu plus one standard deviation and mu minus 1, we know that that comprises of 68% of all outcomes if it's normally distributed. So just to be clear there, that is a normal distribution, right? In fact, if they sort of write X is normally distributed with mu and standard deviation, so variance, right? This guy here signifies that it is normal distribution, 68%. And then by the same token, so you probably remember these ones where that's mu plus 2 and mu minus 2, right? That is 95%. And then by the same token, if I take another standard deviation away, so mu plus 3 and mu minus 3, that represents 99.7%, right? And what's important there is for you to then say to yourself, well, if that's 68% and it's symmetrical, right? There is a symmetrical property about the bell curve, then halving that, 34% would lie one standard deviation below, and 34% on average is one standard deviation above. And then you can sort of work out what the areas are, what percentages fit into each one of these chunks. So for example, if 95% divided by 2 is 47.5, if that 47.5 is over here and that's already 34, then we know, just by subtraction, that's 13.5, and that's 13.5, right? 99.7, so that's like 48.95, right? So then doing your maths there, that there is 2.35. Yeah, and then 2.35% there as well. And because that's 99.7, then the remaining parts there, the outliers, would be 0.3. So divide by 2, divide that by 2, right? So normality basically says after 3 standard deviations away, it's 0.3 on the outliers. And it's 0.3% in total, so it's 0.15. So these parts here comprise of all the necessary components above and below the mean. Now, comparing that to a standard normal distribution, right? So for a standard normal distribution, which is generally written as, so if normal with mu and sigma squared is variance, so then that will be 0 and 1, right? Then what's clear here is that the probability, because of because of its symmetry properties, right? If I take the probability that Z is less than equal to 0, right? So basically everything from here downwards, right? Assuming this guy's 0. So if it's normal, the mu is 0, 0 minus 1, that's -1, that's +1. This guy is -2, this guy's +2, and this guy's -3 and +3, right? And everything below 0 is 50%. Then by this, if I was to take probability of Z, let's say, for example, less than 1, right? So from this point here, this line here, backwards, I basically take the 50 and then I add the 34%, which becomes 84%, right? Pretty straightforward. So basically, I want to quickly jot down, so you can have it here, because I'm going to use this to compare it to the table of values, just to give you that connection, right? If it's less than 2, so from this line on, if I take the numbers, the 50% plus the, what's that, 47.5. So 97.5% is what I'm expecting to be less from all the values. So just to be clear, I'll highlight and I'll remove it. Everything from here backwards, sorry, including, not including that, sorry. From here backwards, right, this bit here should all equal to 97.5%. Yep. And then last but not least, just to complete our picture here, less than 3, so less than this line backwards, so include the 2.35%, so that's like 50%, so that half there, plus the 49, I think I said that wrong before as well, it's 49.85%, yeah, which gives us 99.85%. Right, so basically another way to say that is if this was the HSC and the average was 70 and it's normally distributed and the standard deviation was 5, right? Basically 3 standard deviations above, let's say 70, so plus 15 will be 85. The probability of all students, if it's normally distributed, that are less than 85 marks, is going to be 99.85%, which means there's a 0.15% of students that are above 85 marks. Yeah? Now, and for completeness, if I was to produce the Z values, which are less than -1, right? You basically take the 50%. Yeah, you can imagine that I'm going to take this 50% here, and then basically subtract, if the -1's over here, subtract the 34%, right? To get the areas less than -1. So subtract 34%. So once again, let's go quite quickly on this. That's 16%. Probability Z less than -2. By the same token, instead of basically these pluses over here, be minus. So be minus 47.5%, which is at 2.5. And last but not least, Z minus 3, 50%. Minus the 49.85, which we know to be 0.15%. Now, it's actually quite useful, and you'd be sort of behind the 8 ball if you don't, to try to memorize these key numbers, right? Yeah, so instead of the 68, 95, and 99.7, which is fine, right? You should remember those. These numbers here are actually quite useful, yeah? So what I'm going to do, just see if I can zoom out. So I want to then connect this to a standard normal table, which I've sort of prepared, and I'll just leave it here just to show you how these numbers tie in. So this is, I mean, you can get this anywhere. I've just produced my own, and you can get it from Cambridge textbooks or Fitzpatrick, etc., etc. So you can see these numbers here connect to the numbers in the table. And I just want to show you that obviously these numbers here are rounded and approximated, while here it's a bit more exact to full DP. You can sort of see probability Z is less than 1. That's 1 there with a whole number of 0. So that's that 84% there, right? That's the same sort of number. That's the approximation. That's the exact, oh, sorry, exact to full DP. When P equals a 2, 2.0, that's this one. So you can see it's not exactly 97.5%, it's 97.72. And similarly, 3 99.85 is actually 99.87 exactly, and well, just for completeness there, that's 0.5. Right, and then how do you get these negatives? Please remember two rules for me, right? Two rules. The first one is, whenever you have a z, right, that's less than or equal to, let's say, -2. Yeah, so that's basically this area here. You can sort of see, right? And I'll get rid of it. The probability less than 2 is the same as the probability greater than 2, right? Yeah, so the first one is that to approximate that, that's like 1. So let me just get rid of the highlighting so it doesn't. That's the same as 1 minus the probability that z is less than, also greater than 2. Yeah, and how would you do greater than 2? You basically do 1 minus, right? Because 1 being the 100%, 1 minus anything less than that, right? So I would go, that's the same as, oops, pen, 1 minus that. That's the same as 1 minus, in brackets, 1 minus, right? The probability that z is less than 2. Yeah. So in this case, put bracket around that. Yep. So that actually says to me, let me see. So the probability of less than that is the same as 1. Oh, sorry, I've got that wrong. So let me just get rid of that. Equals to that, which is the probability that equals to 1 minus that. Perfect. Yep. And you can get that from the table. So 1 minus this would give you the less than -2. In other words, to get these guys here, right, it's 100% minus these three numbers here, which will get you the number. So hopefully that makes sense. So whenever you need to do positive values, this table here should capture well, anything that's significant, because you can see anything bigger than 3.9 on the z values goes to 100% anyway. All the negative numbers, you use the fact that negative is equal to greater than, which equals to 1 minus. So it's basically 1 minus whatever values are in this table. So if you wanted -2, it's the same as 1 minus +2, right? As a concept. Yeah. Now, if that's okay, I want to do a quick example, right? Where some people in my class were asking me this in some of their schoolwork. So I thought I'd do a question that sort of says this. So the questions that they gave me actually generally has context, like, you know, it's to do with the size of cats, the weights of cats, or the lengths of certain sticks, etc. But let me just give it to you in its pure mass form, right? So if a variable was normally distributed with an unknown mu and an unknown variance, right? And there's two facts given, that the probability that this variable is greater than 11.2 was, let's say, 2.5%. And then the probability that this random variable was less than or equal to 6.7 is equal to 16%. Yeah, find mu and sigma. Now, that's all that's given. And a lot of people, I guess, don't really know how to start this process. A very good thinking point, right? Starting point is that if they give you something like this, a very smart idea is whip yourself up a nice normal diagram, normal curve, where that's obviously some unknown mu in this case. Now, what did they tell you here, right? The first fact that they give you is that when x is bigger than this is equal to 2.5%, right? So on your diagram, that can only mean somewhere over here when x equals to 11.2, right? This area here is 2.5%. That's what this fact is telling us, right? So for some number greater than 11.2, right, when my x value, not z, right? So I can't really use my table at the moment because this is talking about normal, not z, which is standard normal, right? When x equals 11.2, it's 2.5%. And then also the second fact here, when x is less than 6.7, less than, it's 16%, right? Now, students always ask me, how do I know where I'm at? If it's 16%, right? 16, if this is 50 over here, right? That's 50%. to be less than, so that's going to the left, right? And it's only 16%, I have to be over here somewhere, right? So when x equals to 6.7, this area here is 16%. Now, as an example, if they said it was not 16, if they said it was like, let's say 76%, then I know I'll have to come over here because 76 is bigger than 50. I'll have to be over here somewhere, right? Yeah, because it's less than. So the key points to note is this one here tells you it's greater than, so I have to be on this side, and 2.5% is a small number, so I'm just this little section over here. Less than in the second bullet point is on this side of the graph. 16% is a small fraction less than 50, so I'm just over here at 6.7. Now, what's my aim? My aim is to find mu and sigma. So what I'm going to, it's very hard for me to work with x, right? I don't really have any metrics that tell me that relate to percentages with x, but I do have metrics that relate to z. So I'm going to convert each one of these statements of x into a z statement. So I'll show you what I mean by that. So using the first bullet point, right, of x greater than 11.2 equals to 2.5%. Now, I'm going to leave the 2.5 for now. I'm going to look at this statement here. I'm going to convert that to standard normal, right? So check this out. So when I convert this to standard normal, I get PZ. So to get from X to Z, right, please remember the formula. The formula being Z equals to whatever X you have minus mu over sigma, right? So remember that, please. That's your conversion from normal to standard normal. Yeah. In other words, that's how you standardize your scores. Yeah? So then this becomes greater than 11.2 minus mu over sigma, which is missing, right? That's perfectly fine. Yeah. Now, remember I said to you when it's greater than, if I flick back, right? So greater than is the same as 1 minus. So I guess what I'm trying to say here, right, is, sorry, where is it? Back here. Yep. So the greater than there is 2.5%. Now, 2.5 is not, in this question, it's not coincidence. 2.5% is a nice number given to us, and we've seen that before, and you can see it over here, right? There's a 2.5% there. Yeah. So in other words, it's less than -2 on my diagram, right? So it's basically, it's the same as if I was to draw a graph. This 2.5% is over here right now, which I know from my table is exactly the same as, so when Z equals to 2, that area there is exactly the same as this area here, which is equal to -2. Yeah. In other words, this guy here, if I was to convert this statement into a less than, because why do I want less than? Because less than is what I can use my tables and my values for. Greater than, it's not what the table's built for, right? So I'm going to convert this into a less than statement, right? Where I know that that's the same as 2, which is 2.5%. Yeah, these guys are equivalent values. In other words, this is equal to 2, right? It's the same expression. It is the same expression. You can see the areas are the same. Now, why am I doing this, guys? Let's see if you can see. Because if I make this green statement here equal to the 2, times a 2 up, can you see where I'm headed with this? I've got 2 unknowns. I've now got one expression for me to potentially solve simultaneously, right? So if I sort of make mu the subject, there, chuck it over, move that 11.2 minus 2 sigma, I now have my first equation to solve simultaneously. Now, once again, how did I develop that? I basically said to myself, well, I can't work with x because that's just normal. I'm going to standardize it and then say to myself, well, if this is greater than and it's 2.5, that's mathematically equivalent because it's standard normal to this area under here with a less than, where that's 2. So if this is 2 and that's 11 minus, these two guys are equivalent, right? And that gets me my first equation to solve simultaneously. Yep. So I'm just going to zoom out. Let's do our second point. So that gives us our first equation. The second bullet point then of probability of x less than 6.7, which equals 16%, right? This guy will give us our second one. Now, once again, I need to standardize this where P of Z. So what do I mean by standardize? I need to apply this formula where it's 6.7 minus mu over sigma equals 16%. Now, just like before, I'm going to whip up a quick diagram just to check where it is. So less than, perfect. I need less than, right? I can't really work otherwise. 16%, right? And that Z now. See what value that is, right? 16%. So let's have a look at our graph over here. You can literally look at these values. So 16% is once again a nice exact value, but you can also see 16% falls over here, right? Yeah, if you add up these numbers here, -1 is what you want. -1 has all three areas adding up to 16%. So -1 there. Yep. So the Z value is -1. It's less than. So basically, I'm going to do exactly the same. That I know that this guy is equivalent mathematically to -1, which is 16%. So the 16% basically tells you, right? The information it tells you which Z value is equal to. So once again, I equate these two to get my second equation to solve simultaneously. Yeah. So once I equate it, let's see what we get. We get 6.7 minus mu over sigma equals to -1 times the sigma up. Negative sigma, make mu the subject again to solve simultaneously. And that is our second equation to solve simultaneously. Yep. So I'm gonna just shift some of my diagrams up a bit so I can actually do everything on this page, if that's okay. Yep. So if I then say to myself sub 1 into 2, I should be able to go 11.2 minus, was it? Minus 2 sigma equals to 6.7 plus sigma. I think if you minus it over, 4.5 equals to 3 sigma. Sigma is 1.5. Brilliant. And if you sub that into either this one or the other one downstairs, then mu should be equal to 8.2, right? And that's my answer. Yeah, that's my answer. This guy and this guy. So, just to quickly recap, there is a connection between what you've used to see in the 68, 95, 99.7 and what the standardized table looks like, right? There's an absolute connection. You can see it in these three numbers here relating to these, the first column, because they're whole numbers, right? The rest are like, 1.5, etc. While these ones here being negative, it's almost like 1 minus that first column, right? Second point is that sometimes I might give you a question where mu and sigma is missing, right? And you're going to have to use the standardized numbers to do. So if they give you X, standardize, and then find out what the value of Z is for you to do it. Now, the harder questions are the ones where these numbers here are not whole numbers, right? So the percentages that you see of 2.5% and 16 are not the ones that you've seen before in your, which are derived from your 68, 55, 95, etc. Yeah, that's when it gets a bit harder. We can deal with that at a later video, but basically, like say, for example, if this was like 2.5, then it is a harder question. So just keep that in mind. Hopefully that's useful. If you like this video, please click on like and tell your friends to subscribe. Otherwise, I'll see you guys in the next video. Catch you guys later.